The time series to graph library is a Python library we are developing within the Graph-Massivizer project. It aims to democratize access to state-of-the-art techniques for turning time series into graphs and generating time series from such graphs. Among the implemented time series to graph techniques, we can mention heuristics such as natural visibility graphs, horizontal visibility graphs, and quantile and ordinal partition graphs. Once a graph is generated, it can be traversed to generate novel sequences that resemble the original time series patterns. Here, we show some of the documentation we published. We distinguish 4 core components. First, we provide some interfaces and implementations to read time series data and make it available to our core objects. Second, a set of core classes model time series and their graph representation, providing also ways to extend existing functionality by implementing strategies and visitor classes. The last 2 components relate to strategies that allow us to turn time series into graphs and graphs into time series. To facilitate the understanding of the methods and promote the adoption of such techniques, we have also created a tutorial. In this case, we showcase how stock information can be processed to create graphs representing particular stocks, Apple and Amazon, how the relationships between them can be encoded, and how the resulting graphs can be traversed following multiple strategies to produce novel time series that still follow patterns and dependencies from the original ones. Let's jump into it. After importing the library, we should indicate the library how to access the time series data, and can use a builder to specify how the time series to graph conversion should be performed. We may even have multiple views on the same time series, and want to combine them into a single graph. Once the graph is created, we can specify heuristics that traverse such graphs to produce novel, synthetic time series. These generative methods support working with univariate and multivariate graphs. Since we started the library development, we have also been proactive in disseminating it and applying it to multiple real-world use cases. Here, we show a poster we recently presented at the KDD 2024 conference. In the poster, we briefly describe some methods we implemented at the library and invite the attendees to use them in their projects. Among real-world applications, we successfully applied it to predict compute node downtimes at high-performance computing data centers, and we are now working on use cases related to mining, weather, finance, and the automotive industry. Time series to graph is not the only library we are developing. We are also working on the Go Network library, a library that aims to implement a wide range of graph sampling and summarization techniques. We won't be showcasing this library in detail, but rather jump to some work we have been doing regarding summarization. We have some exciting results to share.
One of the functionalities offered by the Graph Scrutinizer is the ability to create summary graphs from an input graph at various levels of detail using the k-forward bisimulation algorithm. These summary graphs reflect some information of the original graph, but are often magnitude smaller in size. This makes summary graphs a suitable candidate for scaling downstream tasks such as machine learning, where it has been shown to be effective at keeping a low memory footprint and at lowering the energy usage. To run our program, which is written in C++, simply provide a graph in n-triples format. For this demo, a subgraph of SemOpenAlex is used. Our program will first separate the URIs from the graph topology. The latter is stored in a custom binary format to reduce memory usage. Now the actual k-forward bisimulation algorithm will run. It will create new summary graphs until it has found a fixed point at which the full bisimulation is found. The summary graphs can now be used in downstream tasks such as machine learning in Python. Our program also provides some statistics to analyze the output. Apart from the C++ implementation, we also have a concurrent version in the Go programming language that is yet to be tested at scale.